Incomplete truth tables. Sometimes we wish to manage optimization of digital logic functions that have more than 6 input variables. Up to 6 input variables we can manage with Karnaugh maps for optimization, but beyond that, working with digital logic can be a little bit dicey with optimization. So we have to break the problem down into smaller components. Let's look at an example of a kind of function that we might want to consider. Let's call it an encoder. For example, an encoder takes an input of maybe k wires and then outputs n wires. The relationship between k is a log base 2 such that n is equal to log base 2 of k. So this is for where k or n is equal to, well actually, k is equal to 2 to the power of n. In the encoder, we wish to define the function as output the integer that corresponds to the active input wire. So what does this mean? Let's say we have an 8-bit encoder. 1, 2, 3, 4, 5, 6, 7, 8. We can call the inputs I0 through I7. And then we have output bits. What is log base 2 of 8? It is 3. We have O0, O1, and O2. 8 input bits and 3 output bits. We have a constraint. Assume only one input bit at logic 1. While all others are at logic 0. So if we had an input, say here, 0, 0, 1, 0, 0, 0, 0, 0, this would be a valid input. Our input value that's set to 1 is I2, so the output vector will be here at the output. It will be 0, 1, 0, like so. This corresponds to input 2. If we had an input vector 0, 1, 1, 0, 1, 0, 0, 0, we would have a 1 set in more than one location. We would have a logic 1 set in more than one location, which violates this constraint. So this would be an invalid vector. We could assume that this is a don't care condition. So how do we manage this kind of a digital circuit? How many input variables do we have? We have 8 input variables. But there are only 8 possible outputs. In our incomplete truth table, we can list the outputs we can list all rows that have non-zero outputs then. So let's list it. I7, I6, I5, I4, I3, I2, I1, I0. And then we have output O2, O1, and O0. 2 to the power of 8 equals 256 input combinations. Do we want to list all of these out? For this circuit, however, the answer should be a no, because if we list all of these out, it will take an exceedingly large amount of time to do by hand. And besides, the majority of these inputs are illegal. We can assume that they are not going to be used in the actual circuit. So, how do we list this in an optimal fashion? Well, we can say that we have a 0 input for 7 of the bits, and then a 1 input here. This corresponds to input 0. So we will list the input number as 0. Then we can list the next input, where 1 is on input 1. And then the output from the encoder should be 0, 0, 1. There's a pattern now. Input 2 has outputs 0, 1, 0. Input 3, I3 is 1, implies that we have output 0, 1, 1. We just follow the pattern. Input 4 is set to 1, and the output is 1, 0, 0 in binary. Input 5 corresponds to 1, 0, 1 in binary. Input 6 1, 1, 0 in binary. And then input 7 corresponds to 1, 1, 1 in binary. Now this constitutes all the possible legal outputs and all possible legal inputs. Everything else is just ignored. Now, what do we do with the remaining outputs, though, or with the remaining input combinations, however? We can assume output is 0. So now we need to see where is the input, where are the output bits 0, 1, and 2 equal to 1. Anytime the entry is unlisted, the output bit 0, 0, 01, or 02 is equal to 0. Let's look at 00. We have 4 terms for 00 that we need to think about. We have this row where it's 1, this row where it's 1, this row where it's 1, and this row where it's 1. 00 equals I7 prime, I6 prime, I5 prime, I4 prime, I3 prime, I2 prime, I1, and I0 prime. This is now ORed with I7 prime, I6 prime, I5 prime, I4 prime, I3, I2 prime, I1 prime, I0 prime, or I7 prime, I6 prime, I5, looking at this row here, I4 prime, I3 prime, I2 prime, and I1 prime, and I0. And then we can OR that with I7 and I6 prime and I5 prime and I4 prime and I3 prime, I2 prime, I1 prime, and I0 prime. So one simplification that we can see is that all the odd numbers are possible to be 1, but none of the even numbers. So we can say that it's equal to O0 ANDed with I6 prime, I4 prime, I2 prime, I0 prime, and this ANDed with the 4 possible terms, I7 prime, I5 prime, I3 prime, I1, or I7 prime, I5 prime, I3, I1 prime, and then there are two more terms here. And I'll let you worry about how to derive those. The input variables, each term is a minterm and requires all the input variables to be included unless there's a don't care. So we don't have any don't cares listed here. We have to list all the variables for each term. Let's try O1. O1 O1 is O1 is in this column, and we have the two inputs that we're interested in are here are I2 and I3, and then I6 and I7. Those are the variables we're most interested in. I2, I3, and I6 and I7. So O1, we're going to say I5 prime and I4 prime because these always need to be 0. I1 prime and I0 prime. These are always 0. These values are always going to be 0. Otherwise, you're not going to see an output 1. So now we need to think about I2, I3, I6, and I7. So I7 prime and I6 prime, I3 prime, I2, or I7 prime, I6 prime, I3, I2 prime, or I7 prime, I6, I3 prime, I2 prime, or I7, I6 prime, I3 prime, I2 prime, and then close parenthesis. And for our last bit, we need to think about I4, I5, I6, and I7. So the 4 bits we're interested in are in these 4 rows here. Let us try listing those now. We can list it longhand again, like we did for O0, but I'm going to skip that and do a direct optimization instead. We'll say O2, and we know that the bottom 3 inputs are always going to be 0. I3 prime ANDed with I2 prime, ANDed with I1 prime, ANDed with I0 prime. What are the other possible input combinations? I7 prime, I6 prime, I5 prime, and I4. The first term. I7 prime, I6 prime, I5, and I4 prime. Or with I7 prime, I6, I5 prime, I4 prime. That ORed with our final term, I7, ANDed with I6 prime, ANDed with I5 prime, ANDed with I4 prime. Each row that outputs a 1 corresponds to a term in the Boolean expression. Each row in truth table that outputs a 1 a logic 1 corresponds to a minterm in the Boolean expression. And this technique can be used to express a larger Boolean function that has more input variables than 6. Notice that we can put the output function very concisely on a single line of text for O1 and O2. If we took the time, we could put O0 on a single line of text as well. Let us look at another example for an incomplete truth table. Let us think about the if-else and case statement in programming. The key for using a multiplexer is to choose either one input value or another, and then output it. So the typical block diagram symbol is like this. You have some number of inputs and some number of controls. So if you had k inputs here, you would have n inputs here. Right? So it's similar to the encoder. I'm focusing on these powers of 2 kinds of circuits because they are fairly common in development of digital logic, and very much need to be handled with the incomplete truth tables. So let's see here. We have an output O given value at selection bits S. So this is an n-bit value, and we'll call it S, which is equal to a vector of bits, S n minus 1 to S0, right? We then have k-bit input, and we choose input bit S. So let's say, for example, more specifically, a 6, actually let's do a 5 input multiplexer. Let's make this a little bit easier. We can also call a multiplexer a mux. It's a shorthand name for it. So here is our mux symbol. We have I0, I1, I2, I3, and I4 for 5 possible inputs. And now we need n equals log base 2 of 5, ceiling equals 3. So we have output O. Actually, let's put the O here. And then we need 1, 2, 3. We have S0, S1, and S2. How many input bits do we have? 5 plus 3 is 8 again. So we have I4, I3, I2, and I1, and I0 for our input bits. Our selection bits are S2, S1, and S0. Output is O. How many possible inputs are there? There are 5 possible inputs, and they are selected by S. Let's list them now. Input 0, input 001, input 1, input 2, 010, input 3, 011, input 4, 100. We do not have any other possible input values that this multiplexer will select. Assume S is less than or equal to 4 at all times. Remaining inputs are don't cares. So now that we've already taken a look at all the possible input combinations that are pertinent to this 5-input mux, we can say, well, we don't care about any other input values for S0, S1, and S2. No other input combinations matter, so let's forget about them. So we want O to be a value of 1 when on 0, 0, 0, or we want it to be a value of 0 when I0 is 0. So we can say there's a 1 here. When there's an input value of 1 on I0, then we will see an output of 1. if there's an output of 0, then it will be an output of 0. We could list the 0 case, but because there's a 0 here, and we assume unlisted outputs are 0, are logic 0. We don't need to list the row where I0 is equal to 0 and we are selecting that bit. So we are just going to ignore it. Now another question, do we care what the values are of I1, I2, I3, and I4? Do we care what I1, I2, and I3, and I4 are? No, we don't. So we can just mark these off as don't cares. On the next input, I is 1 corresponds to an output of 1 when bit 1 is selected, and we don't care about any other input bits. Note that we don't write down the row for I1 is equal to 0 because the output is equal to 1. And the output of 0, we don't write down the output of 0 because the unlisted outputs or unlisted rows are always 0. So input 2, we don't care what I0, I1, I3, and I4 are. We output a 1. For input 3, we don't care about 4, 2, 1, and 0. We output a 1 again. Finally, for input 4, when that is a 1, we don't care about any of the other inputs, and our output is a 1 again. So now we have 5 rows. How do we draw the Boolean expression? Each row corresponds to a term in the truth table. So O is equal to, let's look at this row. Well, we have S2 prime, S1 prime, S0 prime, and I0 is equal to 1. So this first row is taken care of. Let's look at the second row. We OR first term with S2 prime, S1 prime, S0, and I1. Don't cares we do not include in the term because they are not affecting the term at all. So our second row is finished. We have written that term. Our third term, or S2 prime, S1, S0 prime, ended with I2. We'll mark this off. The next one, we will OR with the next term, S2 prime, S1, S0. And we will end that with I3. Our fourth term is taken care of. Finally, we will have our last term, S2, S1 prime, and S0 prime. We will end that with I equal I sub 4. And we now have a Boolean expression which expresses the output O for a 5-input multiplexer. Notice we have 8 input variables, but the Boolean expression has 5 terms. This is because only 5 possible input combinations output a 1. If you have a Boolean equation that is able to output 1s for only a small number of terms, then using an incomplete truth table could be a very effective way to implement your function. Other places besides multiplexers or encoders where this might occur is in a control block in a central processing unit. So how does a CPU work? Well, say you would have a mathematics block, arithmetic logic unit, and there would be some control here. You may have a register file here. That comes like this, and it cycles around. And maybe you have a multiplexer here. This comes from, say, instruction memory. And we have a program counter here. So the program counter dereferences the instruction that we wish to operate on. Now the problem is that the register file has some control signals that tell it which register values to output. And the ALU has some control signals which tell it which operation to execute. These control signals need to be decoded from the instruction. So we can have a control block here that tells the program counter as well, the register file, and the ALU, arithmetic logic unit, how to function. If K instructions, then you'll have on the order of K entries in a control block truth table. So this is the method that was used traditionally to handle control in processors in early days when CPUs were developed by hand. The time that this video is being prepared is in 2019. Nowadays we use Verilog or VHDL to develop a high-level control system. And we can use programmatic statements to develop it, and then a compiler automatically generates the digital logic, which is much faster and easier for the end user. But to handle control back in the 1970s, companies would manage control blocks this way and would implement logic as two-level networks using digital logic gates and programmable logic arrays. So this completes the introduction to incomplete truth tables.